So last time, if you recollect, we were talking about distortions as a signal propagates through some channel, right? We did our discussion in connection with baseband transmission. That is, a signal is transmitted through a channel, and we found that for distortionless transmission, the signal at best should be subjected to some attenuation and some propagation delay. If that is the case, the received signal is perfectly acceptable to us as a replica of the transmitted signal, and we are quite happy. If, however, the amplitude characteristics of the channel are not constant over the frequency band of the signal, or the phase characteristics are not linear function of frequency over the bandwidth of the signal will undergo either amplitude distortion or phase distortion, right? Both these kinds of distortions are known by the name of linear distortion, right? As against this kind of linear distortion, we can also have a kind of nonlinear distortion which will arise if there is a nonlinearity present anywhere in the communication system. It could be at the transmitter, it could be in the channel, it could be at the amplifier. Of course, the most common source of nonlinearity is the transmitter, power amplifier, and the receiver mixers of the receiver, right, which we will discuss later. So now we shift from baseband transmission to let's say band pass transmission, right, where the message signal is not transmitted directly, but the information contained in the message signal is embedded onto a carrier, and this carrier is what propagates through an appropriate channel. Okay, and we have already discussed why there is a need for such a thing, right? If you restrict yourself to only baseband transmission, there is only so much you can do in as far as communication, electrical communication is concerned. You can't transmit many signals over the same pair of wires. For example, in telephone communication, as you know, a separate pair of wires is required to carry out transmission from your home to the exchange. You can transmit only one signal if you don't modulate your signal, if you don't frequency translate your signal, right? You require a separate pair of wires for every such signal transmission. Whereas if you were to do modulation, you could frequency translate various signals by different amounts and have non-overlapping spectra and transmit all of them together, right? That's one of the advantages of modulation. Another advantage that we discussed was, if you want to propagate the signal through a medium like space, right, free space or atmosphere, you need to generate radio waves. You need to radiate radio waves, right? Radiation of radio waves can be done efficiently only if the size of the antenna is comparable to the wavelength of the signal, right? For a 4 kilohertz bandwidth voice signal, the wavelength will turn out to be of the order of something like 750,000 meters, right, which is too large an antenna size to try to use in practice. So there are all kinds of advantages. These are just two that I mentioned here again, of carrying out modulation or using modulation as a means to translate the frequency spectrum of your signal before you actually transmit, right? And that's the subject we'll start with now. This is analog modulation of carriers. So as we have seen earlier, there are several advantages of modulation. I'll just repeat them for the sake of completeness. These are things that we have discussed earlier, even today again, so I'll just mention them. Ease of radiation is one, multiplexing is another, convenient signal processing is another, and noise reduction is one more reason why we may want to do modulation. Right? So these are some of the reasons why we would go for modulation. We have discussed this today again. We have discussed this today. This I'll just briefly mention once again for your benefit. It may be more convenient to carry out signal processing in a particular frequency band as against some others, right? For a particular application, right? Suppose you have a wideband signal being transmitted, then it is convenient to embed this onto a fairly high frequency carrier, and then it turns out that you may have technology. You may have technology for carrying out signal processing at the receiver and the transmitter around that frequency with a certain bandwidth than at another frequency, right? So therefore there is a reason to use a particular frequency because technology to handle those frequencies is available, be it microwave frequencies or they be in the HF range or VHF range, right, or optical frequencies, whatever they may be, right? So depending on the kind of technologies that are available, you may like to use a particular frequency band for a particular carrier frequency for your signal processing requirements. Similarly, certain frequency bands may be more noise free than certain other frequency bands, right? As we have seen, the noise that is present in the channel is a frequency dependent phenomenon. It is not the same at all frequencies, right? Also the channel has different characteristics at different frequencies. For example, at certain frequencies, microwave radiation gets absorbed by the water vapor present in the channel, in the atmosphere. So you like to avoid such frequencies, right? So depending on where you want to work, what you like to choose appropriate frequencies. So noise reduction is another reason why you may like to use one particular carrier frequency rather than some other. The information bearing signal is typically a baseband signal in all these applications, right? And we have mentioned these before. This could be typically voice, this could be picture, this could be data, right? These are the three most commonly forms in which information is available to us and we need to transmit. So they are usually low pass in nature, right? So these are usually low pass. Low pass term is not used only to specify filters, which is the most natural. When you say low pass, it normally refers to something is being passed through something, right? And therefore it has a connotation of being a filter. But it has come to be accepted to use terms like low pass even for signals, not necessarily only for systems. So if we say a signal is low pass, essentially we are saying that its spectrum is centered around 0, right? So of course there is another alternative name for it. We also call such signals as baseband signals, right? And as we just discussed, because of this very nature, we require these signals are not suitable for direct transmission. It is preferable that they modulate, this information is embedded onto a carrier and then transmitted, right? That we just discussed. But remember again that the bandwidths of each of these kinds of signals is different, right? This is a small bandwidth signal comparatively, this is a much larger bandwidth signal, and this is a variable, right? Depends on the rate at which you are transmitting data, right? It could be low bandwidth, it could be high bandwidth. For example, data communication that you carry out over telephone lines. Do we do data communication over telephone lines? Right? Through your fax is not the only thing. You connect your computers through a modem, right, to connect to other computers. And the network that you are using there is a telephone network, right, which was not designed for telephone data communication. It was designed for voice communication, right? But yet we have found means of using the same small bandwidth to transmit data at fairly good rates, right? For example, today you have modems which go up to 56 kilobits per second, but the bandwidth available is still the same, 4 kilohertz, right? In a bandwidth of 4 kilohertz, you are able to transmit 56 kilobits per second, and that's possible because of proper use of proper kinds of modulation and coding schemes, so that it's possible to use this bandwidth efficiently, right? So the nature of the data will depend on the bandwidth required by the data will depend on the rate at which you need to transmit data, right? If you have a high data rate application, you may require tens of megahertz of bandwidth, right? If you have a low data rate requirement, you can manage with a few kilohertz, like we do in telephone modems, right? So bandwidth requirements depend on message type, right? So these are things which we have discussed before, but it is pertinent to review them once again so that things are seen in their proper context. Now, as we go along, we'll discuss a number of different kinds of modulations. Well, more specifically, there will be at least three different basic kinds of modulation that we'll discuss, namely the amplitude modulation, the frequency modulation, and phase modulation of carriers, of which the first kind, there are large variations of the first kind, namely amplitude modulation, all of which are studied under the general title of linear modulations, right? So we'll start our discussion with what is typically known by the name of linear modulation. Okay, and now we'll develop a framework to study various kinds of linear modulations. Okay, to do that, let's introduce some very simple basic notation that we'll use. Typically in our discussion, we'll denote the message by a waveform denoted by m of t, right? So typically when I write m of t, it's a signal which represents the message waveform, right? So this is the message waveform. I shouldn't really use the word message because message has different connotations, so we'll call it message waveform, right? Some signal as a function of time which contains the information of interest which you want to transmit. The carrier, as we have seen earlier, we have discussed earlier, is typically a suitable high frequency sinusoid, right? The exact frequency will depend on the application, right? If it is a microwave link that you are working with, you are propagating your signal on, you will choose a typical frequency in the VHF or higher band, right? If it is the ionospheric propagation that you want to deal with, you will use a frequency less than 30 megahertz, right? Something like your HF band, right? If you are carrying out broadcast in the using the ground wave propagation, you will use it in the medium wave frequency band, right? So depending on what the application is, you will choose your carrier frequency differently. But in each case, as far as this theory is concerned, we will denote our carrier by simply cosine omega ct or some a cosine omega ct, where omega c is the carrier frequency in radians per second, right? Now, as we have learned from our discussion of our review of signals and systems, there is a very basic technique for frequency translation, and that's one of the main objectives of modulation, right? We want to carry out a frequency translation of the message, which is a baseband or low pass signal, to around some other frequency omega c, to convert it into a band pass signal, right? And the basic frequency translation theorem that we have learned about, which we also known by the name of modulation theorem, and now you can appreciate the reason for that name, is what is the basic frequency translation technique that we know of? Just multiply these two signals, right, in the time domain. So this operation therefore is simple multiplication operation which takes a message signal m of t and multiplies it with the carrier a cosine omega ct. This is the most basic and fundamental operation in analog modulation, and particularly linear modulation, right? So this operation is variously known by the names of frequency translation. There are other names depending on the context in which you are using this. This operation sometimes is also called mixing, because you are mixing two signals, right? Of course, mixing is used in a slightly different context, but nevertheless the basic operation involved is the same: multiplication of two appropriate signals, right? And another name is heterodyning. So if you come across any of these names in some context, right, this is what they mean. Basically we are referring to this operation, the multiplication operation. So frequency translation could be carried out using a mixing operation or a heterodyning operation, which basically means multiplication, right, of the two signals. Actually mixing is slightly more than just this, but we'll discuss that as the time comes. Now this basic operation forms the basis of all linear modulations, right, or what we call linear amplitude modulations. So all these linear amplitude variations are basically variations of the mix, the multiplication, the multiplier operation that we discussed earlier. Right? So there are variations of this. Let's discuss these variations now. The simplest is just this process that we have discussed, right? In terms of our starting point could be just this very modulation that we just discussed, namely multiply mt with cosine omega ct. We know that this will lead to frequency translation, as we'll soon again review. This kind of modulation, this is a kind of modulation, is called, as we'll see the name for that, reason for that, DSB-SC modulation, standing for double sideband with suppressed carrier. So this is DSB-SC modulation. So a modulation in which we generate two sidebands. That's what it means, double sideband. We have to understand what the concept of sideband is. In a few minutes we'll do that. And the carrier is suppressed, right? We'll try to understand the meaning of each of these terms that is coming up. The basic signal is the one that we just discussed. The modulated signal x of t is AMT cosine omega ct. Right? Let's try to see why this signal we call by this name. So when I refer to DSB-SC modulation, we are referring to this signal. Message mt multiplies the carrier a cosine omega ct. Right? Before we go into the reason for calling it by this name, let's once again review what would this signal look like, right, physically. Let's say this is your, just for the sake of discussion, your typical message waveforms will not be sinusoids. Typical message waveforms will depend on what signal you are actually interested in transmitting. For example, a voice signal, I do not know whether you had the occasion to look at the waveform of a voice signal on an oscilloscope or on a computer generated on a computer, right? It doesn't look like a sinusoid at all, right? It looks very different from that. But for the sake of our simple discussion here, let's assume that our message signal is a sinusoid of low frequency. Right? Since it is to be low pass signal, we'll represent it by a low frequency sine wave. Right? So let's say this represents your MT. Right? And let's try to now depict the modulated signal, which is MT into cosine omega CT. Right? We have discussed this earlier, but let's just quickly review this. The way to look at it is the following: cosine omega CT is a high frequency carrier. That means the duration of one cycle of the cosine wave is much smaller than the duration of one cycle of the message signal, right? In this particular case, because this is a sine wave also. So we can assume practically that over one cycle of the cosine wave of the carrier, the message signal MT practically remains constant, because that variation happens too fast for it to vary significantly, right? So if that remains constant, what do you see at the time instant t? You see a sine wave or cosine wave of amplitude AMT, right? You can, MT is nearly constant over the whole cycle, right? So effectively, the amplitude that you will see a carrier, basically a carrier with an amplitude of A times MT rather than A, right? That's what you will see. So essentially, therefore, it's clear that as this message changes, you will see carrier of different amplitudes, right? The carrier will have the largest amplitude here and the smallest amplitude here, the smallest amplitude here, zero amplitude at the zero crossings, and so on and so forth, right? So that's something that we already discussed. So it will look something like that. This dotted line represents the what we call the envelope of the modulated waveform, right? Which we already discussed. Because this is a trace of the peaks of each cycle of the carrier, right? So it will look like this. Let's see what will happen to the carrier at this point. I just want to be a little more particular. As we go from one half cycle of the message waveform to the next half cycle of the message waveform, or as we cross the zero in the message waveform, how does the carrier behave here? Just see, the carrier was being multiplied by some positive quantity just before the zero crossing, right? The carrier is now going to be multiplied by a negative quantity just after the zero crossing, right? So can you say something as to what will happen at the point at the zero crossings? The phase of the carrier will suddenly go through a phase shift of 180 degrees. Is that clear? So the carrier will not will continue smoothly, keep on going like this. There will be a certain phase variation by an amount of 180 degrees. So you will start once again like this, and so on and so forth, right? Of course, my picture is not perfect. The carrier cycles are not of uniform duration, but they should be, because the carrier frequency remains the same throughout. So the important thing is that the envelope is this, right? What is this equal to? The envelope in this case is proportional to, so suppose I call this E of t to denote, I'll call this the envelope, this dotted waveform, which essentially gives me the amplitude of the carrier waveform at different times, right? And we already seen that this is, and it's obvious also from this figure, that it's proportional to you are forgetting something. Modulus of MT. The envelope is this. Envelope is not this, right? MT, this is MT. Envelope by definition is this. Envelope by definition is a trace of the peaks of the carrier waveform, right? So that is how you define the envelope. Obviously, like as you can see, in this cycle, the envelope is this, which is the modulus of this, right? Of course, the actual waveform is this.
So can you explain this middle part again, how this 180 phase shift?
Very simple. The question is, he wants to know once again how there is a 180 degree phase shift of the carrier at the zero crossing of the message waveform, right? At the zero crossing of a message waveform, before the zero crossing, the message was positive. So a positive number was multiplying cosine omega ct at that time, right? So immediately after the message after the zero crossing, a negative value is going to multiply mt cosine omega ct, and therefore suppose you had something cosine omega ct. Suppose this instant is called t prime, right? So you had some value cosine omega ct prime minus, let us say, this omega ct prime minus just before this, and after this what do you have? Minus cosine omega ct prime plus. So in going from t prime minus to t prime plus, the sign of the carrier changes, right? That's all we are saying, and therefore this is what you will see.
Do we assume that the frequency of mt is a multiple of omega c, or the other way around?
No, there is no such assumption required. This is something that will happen. I mean, for drawing this waveform, I might have used that, right? But there is no such requirement. This will always happen at the zero crossing, whether or not this is a multiple of submultiple of omega c, right? This will always happen because this property will always hold, right? So this is not a requirement. So when you look at a DSBSC waveform, let's say on oscilloscope, I believe you will go through a communication lab sometime. You must look at this feature carefully, that indeed at the points of zero crossing, the carrier goes through a 180 degree phase shift, right? The carrier looks like as if it has gone through a 180 degree phase shift at the point of zero crossings of the message waveform, right? So that's a typical picture of the DSPSC waveform in the time domain. So this is the DSPSC waveform. So this is a time domain description of DSPSC. We'll soon see the frequency domain description, which is the reason for the name that we have here. So this is the time domain description. The important things that we have learned here are really two. The envelope of the DSPSC waveform will be proportional to A times the message waveform m, modulus of message waveform mt. And the second thing that we have learned is that at the points of zero crossing of the message waveform, the carrier will go through a 180 degree phase shift, right? So these are the two basic characteristics of a DSPSC waveform. Okay, now let's look at the same waveform in the frequency domain by looking at the spectrum of the DSPSC signal, which is a fairly straightforward exercise. To discuss this, let's assume that your message has some spectrum, and for the sake of these discussions, I'll typically assume the spectrum to be real valued, so that I don't have to carry out two plots, one for the amplitude and the other for the phase, right? But it is implied that if required, one can do that, right? Whatever we do for the amplitude plots will also be valid for phase plots. For convenience, we'll take the spectrum to be real itself, so that there is no question of amplitude and phase separately. MFF directly completely describes the spectrum. So let us say M of f is a low pass signal. Again, when I draw a spectrum like this, it is not to depict that the real signals will have such spectra, right? They may have any arbitrary shape, right? Of course, it will be, if it is real, it will be even symmetric, etc. But otherwise, it can have any arbitrary shape. The important parameter here is the bandwidth of the baseband signal, which we are assuming to be B, right? It could be this shape, it could be any arbitrary shape, right? So what is the nature of x of f? As we know from basic modulation theorem, the spectrum of AMT cosine omega ct would be a by 2 into, tell me, m of plus fc plus m of f minus fc, right? I don't think I need to review this, we have discussed that earlier, and therefore the spectrum will look like this. The modulated signal xt would have a spectrum which is centered around one component fc. So if this is 1, this would be a by 2 peak value, and the same thing will happen around minus fc. And this point will be fc plus b, this point will be fc minus b, and similarly on this side. Okay. Now there are several interesting, this is a very simple thing, all of you know this, there is nothing new about this, but we will look at the spectrum and try to appreciate a few things from the spectrum. First thing that we notice is, let's compare the bandwidth of the original message signal, the baseband signal, and the bandwidth of the modulated signal. Are they same or are they different? What would you say? Are they same? Anyone with a confident answer?
That will be twice of the
It will be twice the bandwidth of the message signal. What is the bandwidth here? B, right? 2b if you include the negative frequency axis, but remember negative frequencies are not something real, it is a mathematical concept, right? The real frequencies are basically the positive, I mean just we shouldn't say positive or negative, really speaking we are talking of a spectrum occupancy of b hertz here, right? The negative frequency is an abstract concept, it's an abstraction, right? But in this case, as you can see on the positive frequency axis itself, we have an occupancy of 2b hertz, because this entire spectrum gets translated to around fc and its width is 2b, right? So the first thing that we note is bandwidth of the modulated signal is 2b. So actually your modulated signal has a larger bandwidth than a message signal. Is that a nice thing or a bad thing? From the bandwidth conservation point of view, it is not very nice, right? Now what does it mean? It means that perhaps we are transmitting more information than is necessary to transmit, right? And can we see that happening? Can we see that how it is carrying more information than is necessary to transmit? Look at this basic spectrum m of f itself. As we know, for any real signal, m of f will have some symmetry properties, right? What are the symmetry properties? Its amplitude spectrum is even, its phase spectrum is odd. So if I know the spectrum on one side of the frequency axis, I also know the spectrum on the other side of the frequency axis, right? What I am trying to do in this modulated signal is transmit both the sides, the positive side as well as the negative frequency side. So that's why it occupies a larger bandwidth, right? If I were to somehow transmit only this, I could as well derive the same information by keeping in mind that the actual spectrum would be symmetric around fc, right? Amplitude would be even symmetric and phase would be odd symmetric around fc for a real modulated signal. So if I somehow could use that, I could have conserved bandwidth by reducing it to b hertz only. In fact, we will discuss that later. This is one of the modulation techniques that is used, and it's called single sideband modulation, right? And that is why this is called a double sideband modulation, right? You refer to this portion of the spectrum which lies above FC as the upper sideband. So as if the modulated signal contains two sidebands, side with reference to the carrier frequency, one above the carrier frequency, one below the carrier frequency, and this portion is called the lower sideband. Right? So if you look at the corresponding negative plot, this will correspond to which portion? Upper or lower? Lower, right? Because it has to be symmetric, right? So this will be lower and this would be upper. Yes, please.
So in the empty signal, what is the signal which I'm having? If I take only the right part of the signal, what's the part? Do I get the whole information about my...
The trouble is, for a real signal, I can't get rid of this, isn't it? I can't get rid of this. The real signal implicitly has a negative frequency component because it's just a mathematical notion. I can't get rid of it. The only way I can get rid of it is by converting it to a complex signal, isn't it?
So, but effectively my right part is having the whole amount of information. Which
True, true.
So when I'm putting it in this part, I'm having a bandwidth of 2B, but the bandwidth of 2B is having only that information, which is originally present in the right part. So I'm not getting any additional information as such.
No, what we are saying is, certainly we are not getting any additional information. We are transmitting much more information than is necessary to transmit. That is the point. If you do this, if I were to transmit, let's say, only the upper sideband, that's equivalent to transmitting MF. If I were to transmit only the lower sideband, that's also equivalent to transmitting MF, right? So as far as information content wise goes, I could have transmitted only one of these two sidebands somehow by removing the other, right? For example, I could have removed the lower sideband and the spectrum would then look like this.
But then it won't have the full information.
It will have full information because I know there is a symmetry around FC, right? And I could have exploited that symmetry somehow at the receiver.
So,
if I knew a way of exploiting that symmetry, I could do it, right?
So
we'll discuss that later because that's not today's discussion. That we'll discuss when we discuss single sideband modulation.
So one single.
Yes.
Are the information which we are giving symmetrical, sir? When you call it real?
Well, we know that the properties of a real signal. What are the properties of a real signal? The spectrum has to be symmetric around F. Amplitude symmetric. It is even symmetric for amplitude spectrum and odd symmetric for phase spectrum. So that symmetry will now get translated to FC. Isn't it? When you do a frequency translation, these symmetry properties would translate around FC.
So this is true only for real signals?
And minus FC. Of course, only for real signals. Because in real life, we transmit only real signals. Complex signals we generate, if we need to generate them, as a signal processing tool. Right? We don't start with complex signals. Right? Actual waveforms that you will transmit will be some voltage as a function of time or some current as a function of time. Right? Which are real signals. True. Okay, can we proceed further then? Right. So the first thing that we learn, therefore, about this waveform is that it has an upper sideband and a lower sideband, each of which carries the complete information about the message by itself. However, in this kind of signals, we transmit both the sidebands, and therefore we call it double sideband. It's a double sideband message modulated signal. Now the second part of the name, suppressed carrier. Let's look at that. In this spectrum, does a carrier by itself show anywhere other than the fact that the spectrum is shifted around the carrier frequency, right? Shifted to around the carrier frequency. There is no specific carrier component present as such, right? I mean, by that I mean there is no impulsive component like this at the carrier frequency. The carrier as a signal, there is no component like a cosine omega ct being transmitted, which is a nice thing because that doesn't really convey any information, right? So there is no impulse component at FC. If there is no impulse component at FC, because of that reason we call it suppressed carrier. That is, it doesn't have a carrier component located at FC, right? Of course, the signal spectrum, if it is non-zero at 0, it will imply that there is a non-zero value of the spectrum here, Right? That is true. But this is a spectral density, right? It doesn't mean that there is a carrier component. For a carrier component to be present, you must have an impulse function there, isn't it? Because density, if you have some value of the density, it doesn't mean that suppose I ask you, what is the spectrum, what is the energy present in the signal at any specific frequency? It is 0, because this is an energy density function, right? This is an amplitude density function, right? So the actual amplitude will be proportional to the area under that curve at that point. Area of a single point, area occupied by a single point would be 0, unless there is an impulse present there, right? So since there is no impulse anywhere here, and specifically it is not there at the carrier, we call it double sideband with suppressed carrier. So the other properties that we have just therefore learned are that the waveform has two sidebands, an upper sideband and a lower sideband, and that there is no carrier component. And hence the name double sideband with suppressed carrier. Okay, now let's look at the amount of power that is transmitted by through this waveform. Just quickly looking at some of the basic attributes of this. Okay, transmitted power. How will you calculate this? How do you calculate power? Signal square time integral over some time interval and divided by the time interval. But in general, your message waveform may not be periodic, so we can't talk about a period or anything, right? But if it is not a periodic waveform, you can always do this. Let's say minus t to plus t, right? A square m square t cosine square omega ct, right? dt. This will be the energy of the waveform in the interval from minus t to plus t. So divided by 1 by 2t, and what should you do? Take the limit as t tends to infinity, right? That will be the definition of our calculation of power for an arbitrary signal, arbitrary waveform. So if you were to do that, this would be equal to, in our case, limit as t tends to infinity of 1 by 2t integral of, let's split that cosine, use the trigonometric identity to write cosine square omega ct in terms of the sum and difference components, in which case it will be, what is cosine square? It will be a square by 2 mt into 1 plus cos 2 omega ct dt, right? M square t, yes. So which is consisting of two parts. This is from minus t to plus t. That's the first part of the integral. What can we say about the second part? 0. Right? What is the reason? What is the argument? The same argument which we discussed some time ago. Because m square t is a slowly varying waveform, right? Cosine 2 omega ct can be considered, we can consider this integral as integration cycle by cycle of the carrier, half cycle by half cycle. So over one cycle, you can assume m square t is nearly constant, right? And the positive half cycle will cancel with the negative half cycle, right? So half cycle by half cycle, the value of the second integral would be 0, because cosine 2 omega ct is being multiplied by a very slowly varying function compared to its own rate of fluctuation. Okay, so therefore the second part is the same argument which we had discussed earlier, and therefore what is now, if you take a square by 2 outside, what is left inside the integral? There's nothing but the power in the message signal itself, right? And what is a square by 2? As power of the carrier. Carrier is a cosine omega ct, its average power is a square by 2, right? So therefore you can think of this as nothing but sc into s sub m, where s sub c is a square by 2, which is the carrier power, and s sub m is the integral etc. of the message etc., right? Limit as t tends to infinity. That's the message power. So your transmitted power S sub t is the product of the carrier power and the message power. So I think with this we have more or less analyzed the attributes of the modulated waveform completely. We have understood its time domain nature, what does it look like, right? We have understood its spectrum, we understood the fact that it carries more information than it need to, right? And therefore occupies twice the bandwidth, right? And we also looked at the amount of power that is present in such a signal, right? So that more or less completes our study of the DSPST waveform. The issue that is left to discuss is, all right, we have transmitted this, how do we get back the message waveform empty from it, right? That's the only issue left. Let's look at that now. Okay, I'll just indicate that here today, and we'll discuss it if required in detail next time. So let's see how at the receiver we can recover the baseband signal back. Any suggestions? What do we need to do?
Demodulate.
Yes, how to demodulate. That is precisely the, when I say recover, the process of recovery is called demodulation, right? The question is, what should we do to demodulate?
So you can shift the signal in the frequency domain, and
We have to shift the spectrum back to the baseband, right? How do we do that?
Some multiplying.
Once again, obviously some kind of a multiplication operation is required to be carried out. Indeed, that is the case. The first stage would be, assume that at the receiver we have a replica of the carrier available to us. The carrier frequency is known to us, and we can generate a replica of the carrier. For convenience, let me write 2 cosine omega ct here. Doesn't make any difference. It's a scaling factor. And the received modulated waveform is multiplied with this carrier. Now, what will this do? What will be the spectrum that you will see here? As we saw in the case of modulation, the message waveform spectrum gets translated up by fc and also down by minus fc, right? That's what happens. The same thing will happen to xt. So the spectrum of xt would, after multiplication with 2 cosine omega ct, would translate to a component around 2fc and also 0. So what you need to do is retain the component which is centered around 0 and remove the component somehow which is centered around 2 omega c, which is very easy. So the second thing that we must have in the demodulator is a low pass filter to remove the double frequency component, right? So we'll look at this operation mathematically next time, which is more or less obvious, and then discuss further about the pros and cons of DSPST modulation and demodulation. Thank you very much.